Hey guys, welcome back to Calculus Basics, and now we're going to go a step further in our journey into the derivative to discuss the power rule. So, if you recall from our last video, we came up with the following expression to find the derivative of a function, which is the slope of the line tangent to that function at a given value x. And this is the limit as h approaches 0 of f of x plus h minus f of x all over the quantity h. So, let's draw a graph and label that graph so that we can get a better understanding of how this would work. Okay, so before we start, there's something I want to mention, is that using derivative notation is given by f prime of x, like so, or dy dx, like that. So either one of these is the same, it's analogous, but f prime of x or dy dx, depending on which type of notation you prefer. So, given that we have our function, f of x, of x equals x squared, as seen here. This graph right here. So let's take a random arbitrary point, say x equals 2. So the point would be 2, 4. Yep. And we want to find f prime of x. And we want to find f prime of x in general. And then we can plug in x equals 2 to find the actual slope of the line tangent to the curve at x equals 2. So let's get going by using our formula that we found earlier. So f prime of x is given by limit as h approaches 0 of big parentheses, all of that over good old h, close parentheses. Okay, so the limit as h approaches 0 part is going to stay, but let's see, how can we simplify this? Well, here's an idea. We know what f of x is. F of x is equal to x squared, so we don't need to keep the generic x plus h and f of x. We can sub in our function that we know. So now instead of it being now instead of it being f of x plus h, we have same thing, x plus h squared. And if you think about it, it's the same thing as f of x plus h, because it's the function f of x equals x squared with x plus h subbed in for x, minus f of x, which is just x squared, all over good old h. So you can see where this is going now. Now we have to do some algebra. Let's shift our screen a tad. Oops. Nope, that's annoying. Okay. Okay. So let's do our algebra. So we have limit as h approaches 0 of x plus h squared is x squared plus 2xh plus h squared. We're just expanding that, minus x squared over h, and as you can see, the h's are going to cancel kind of nicely. So let's go to a new line. That was a really bad m. Limit as h approaches 0 of x squared, and the minus x squared go away. So we have 2xh plus h squared over h, perfect. And now we can go one step further and factor out the h from the top. So we have h times 2x plus h. So if you expand this, you get the original expression divided by h. And the h's cancel once again. And now we're finally at the stage where we can plug in our actual limit. So we don't actually need the limit anymore, because since there's no more h on the bottom and h is going to 0, there's no problem with plugging in h is equal to 0. So we're just left with f prime of x is equal to 2x. Okay, so what does this mean? Let's go back to the very start function over here using this knowledge. Okay. So now that we know this, how does this help us? So therefore, f prime of 2 is equal to 2 times 2 equals 4. So the slope of the line tangent to this curve f of x equals x squared at x equals 2, that line right there, slope of that is equal to 4. And if we want a different point, let's say we wanted the point that continued on further, x equals 5. So f prime of 5 is equal to 2 times 5 is equal to 10. So the slope of the line tangent to the curve at x equals 5 is 10. And this is really cool because now our restriction, given that f of x is x squared equals x squared, is not a straight line. This is a curve, and so the slope is not constant, but we're still able to find the slope at specific points, and this gives us the derivative. So this was a lot of algebra. Like, okay, it wasn't that much to be fair, but it took a fair amount of work. Let's see, is there any way we can simplify this? So let's draw out the relationship between the derivative and our original function. And just to get you used to the other form of notation, I'll be using dy dx this time instead. So dy dx is 2x. Should probably, here, let's do write the original function first. So f of x is equal to x squared, and dy dx, which is the same thing as f prime of x, is equal to 2x. So looking for patterns here. Okay, generally speaking, what I notice is, obviously I know the answer, but from here to here, the 2 was moved out in front, and then the exponent was decreased by 1. So basically, if we write this as a general rule, we don't know if this is right yet. F of x is equal to x to the n, then f prime of x would be equal to nx to the n minus 1. So our theory would be that if f of x is equal to x cubed per se, then f prime of x would be equal to 3x squared, which is nx to the n minus 1. So I guess we can try this. Let's give it a shot. So let's just draw a graph it. So this is f of x is equal to x cubed. Perfect. And now we have to do our fun little limit nonsense. Equal to limit as h approaches 0 of, so f of x plus h. So we have x plus h cubed minus x cubed all over h, and then we keep going. Keep that limit in front because we haven't done the operation of taking a limit yet. X plus h cubed. Let's see. So we know what x plus h squared is. That's x squared plus 2xh plus h squared down times x plus h, because we still have a factor, minus x cubed all over h. Could be working. Let's keep going this way. Is equal to, keep the limit in front because we haven't taken a limit yet. Okay, okay, this part I'm going to do the not cool way to make sure I don't mess it up. So we have we'll call h cubed, then 2xh squared, and then hx squared, 0 here. Xh squared plus 2x squared h, and then x cubed. So our final would be x cubed plus 2 plus 1, so 3 x squared, 3x squared h plus 3xh squared plus h cubed. Okay, that's a lot. Minus x cubed all over everybody's favorite variable h. X cubes cancel once again, and then we can factor. So we have, keep the 3's in place, obviously. You can factor out an h here, so they cancel pretty calmly. Okay, so we have h times 3x squared plus 3xh plus h squared over h. H's cancel again. Now we can plug it in. So we have 3x squared plus 3x times 0 plus 0 squared, which is looking good. It's just 3x squared. And that's what we expected to get. All the way over here, we were saying we think it should be that. So it's a nice parallel that we've drawn. So it looks like our formula is holding up, and let's think about why. So when we take the derivative using limit formula, or I guess definition is the proper term to put there. So when we take a derivative using the limit definition, we are expanding a polynomial. We expand a polynomial. And so when we do that, and our x's cancel, so once the x's cancel, and then we factor out an h to get rid of the h on the bottom, we're always going to be left with the degree of the polynomial, times x to the power of degree minus 1, and then a bunch of h terms. And those h terms are going to 0. Those h terms are going to 0. They're canceling out. So we're left with this right here. And as you recall, this is another way of saying is n times x to the n minus 1 if f of x is equal to x to the n. And this right here, f prime of x is equal to n times x to the n minus 1, is the power rule. So whenever we take a derivative in the form of f of x is equal to x to the n, where n is any arbitrary power, we can just use this rule right here instead of doing this long limit definition, because that's tedious, and if the power is like 100, it'll take forever. It'd be impossible. But if f of x was equal to x to the 100, then f prime of x would simply be 100x to the 99. Just like that. It's done. So thanks for watching. I hope this made sense. It's definitely drawn out quite a bit using the limit definition, but I hope it made sense, and we'll see you next time.